4, which is the zeros of the polynomial functions. Here are our objectives. And let's start with the rational zero theorem. If f of x is the following polynomial where it has integer coefficients and p over q is a rational zero f, then p is a factor of the constant term a naught and q is a factor of the leading coefficient a sub n. So you will find the factors of your constant term, which is a naught, and the factors of your leading coefficient, and divide them one at a time by each other. And these will give you all the possible zeros of the function. So again, let me say that. You'll find the factors of the constant terms. So find the factors of the constant term, which they label as p, and find the factors of the leading coefficient, which they label as q. Divide them, and they'll give you all the possible zeros. Let's go in our books to page 386. Let's look at number 7. It says, use the rational zero theorem to list all possible rational zeros for each given function. So number 7, we have f of x is equal to x to the 5th power minus x to the 4th power minus 7x to the 3rd plus 7x squared minus 12x minus 12. So the first thing we need to do is list the factors of the constant term, which in this case is negative 12. Then we're going to go ahead and list the factors of the leading coefficient, which in this case is 1. And then we're going to divide the factors of the constant term by the factors of the leading coefficient, which is a sub n. So first, let's start by listing the factors of negative 12. So the factors of negative 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So positive 1 times negative 12 is negative 12. Positive 2 times negative 6 is negative 12, and etc. So then let's list all the factors of the leading coefficient, which is 1. So it's just plus or minus 1. And then we're going to divide them. So plus or minus 1 divided by plus or minus 1 is still plus or minus 1. Plus or minus 2 divided by plus or minus 1 is plus or minus 2, and etc. And these are all the factors of the polynomial f of x in number 7. All the possible factors. I apologize. Possible factors. Alright, so number 9 says list all possible rational zeros. Use synthetic division to test the possible rational zeros to find an actual zero, and then also to find any remaining zeros. There's 3 parts here. We're going to work all 3 of them. So this is number 9, and it has f of x is equal to x to the 3rd power plus x squared minus 4x minus 4. Part A. Well, part A says list all possible rational zeros, so we need to list the factors of the constant term. So the factors of negative 4 will be plus or minus 1, plus or minus 2, and plus or minus 4. Then you must list the factors for the leading coefficient, which is 1. So those are plus or minus 1. And then we divide them. So all the possible zeros are the following. Plus or minus 1 divided by plus or minus 1 is plus or minus 1. Plus or minus 2 divided by plus or minus 1 is plus or minus 2, and also plus or minus 4. So these are all the possible zeros. And then part B says use synthetic division to find an actual zero from this list. So the fastest way to actually do this, a quicker way, instead of going through all of these possible zeros, here is a quicker way for testing each zero. You're going to first plug the 0 into f of x. Part 2, if the resulting value equals 0, then that value of x, the one you chose from this list to plug into it, is a 0. If not, try another possible 0. So go ahead and take each of these and plug into the original function. Whichever one gives you a 0, that is the one you're going to use for your synthetic division. So let's see here. Which is one that will give us a possible 0, a real 0? If we plug -1 in, so f of -1, and my pen's messing up, is equal to -1 to the 3rd power plus -1 squared minus 4 times -1 minus 4. So this becomes -1 plus 1 plus 4 minus 4, which is 0. So this is an actual 0, so we're going to use -1 in our synthetic division. So there's -1, put your backwards L, now write the coefficients of the original polynomial out, and you have 1, 1, -4, and -4. And let's go ahead and do synthetic division. You go ahead and do it on your papers, make sure it matches what I have. Good, and the resulting polynomial becomes x squared minus 4, because the x term had a 0. Okay, so that's part B, and then part C says, use the quotient found in part B, which is this piece, and find the remaining zeros. So you're going to set this equal to 0, and you're going to solve it. Well, this becomes x squared equals 4, which means x is equal to 2 as well as -2. And also don't forget the -1. So all the possible zeros here, all the actual zeros are 2, -2, and -1. Alright, now let's talk about the properties of roots of polynomial equations. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. If a plus bi is a root of a polynomial equation with real coefficients, then the imaginary number a minus bi is also a root. So what they're saying is, if the imaginary number is a root, its conjugate has to also be a root. If you have a polynomial of degree n, then it will have n roots. And this is the fundamental theorem on algebra. If a polynomial of degree n, where n is greater than or equal to 1, if f of x is a polynomial of degree n, where n is greater or equal to 1, then the equation f of x equals 0 has at least one complex root. And remember, a complex root is written as a plus bi, where a and b are just real numbers. Alright, so now let's look in our books on page 387, and let's look at number 25. I'm only going to do one of these problems since they're done the same way. Find an nth degree polynomial function with real coefficients satisfying the given conditions. It tells us that n is equal to 3. So n equals 3. 1 and 5i are zeros. 1 and 5i are the zeros. And it says f of -1 equals -104. So the first thing we need to do is realize that f of x is going to be written as a times x minus c1, x minus c2, and x minus c3. I know to stop at 3 c's because n is equal to 3, which means you're going to have 3 roots. Now, they have given us 1 and 5i as a 0. The other 0 would need to be the conjugate of the complex number 5i. So the other 0 is negative 5i. So C1 is 1, C2 is 5i, and C3 is negative 5i, the 3 zeros. Now we can fill it in. So we have A as x minus 1, x minus 5i, x plus 5i. The last thing we need to do is find the A, and this is what this information is used for. So the negative 1 represents the x, and the negative 104 represents the f of x. So we have a negative 104 equals A times negative 1 minus 1, negative 1 minus 5i, and negative 1 plus 5i. And then we're going to multiply this out so we can solve for A. Do so in your papers and make sure you match what I get. So this right here becomes negative 2. These right here I'm going to multiply using FOIL. And that's negative 1 times negative 1, which is 1. That's negative 5i, positive 5i, so they cancel out. And I get negative 25i squared. So it's negative 104 equals A times negative 2 times, remember I squared is the same as saying negative 1 in its multiplication, so this is 26. Solve for A, and you get A to be positive 2. Then fill it in. So your final answer is f of x is equal to 2 times x minus 1, x minus 5i, times x plus 5i. You can leave it in this form, or you can multiply these out. And when you multiply those out, you should get x squared plus 25. And then, of course, you can multiply these together. And you should have a final answer of f of x. I have room over here. 1 second. You have a final answer of f of x is equal to 2 times, well, that's x to the 3rd power minus x squared plus 25x minus 25. And then you can distribute the 2 if you wanted to. I'll leave number 29 for you to work. Email me if you have questions. Alright, so now let's talk about Descartes' rule of signs. Let f of x equal the following polynomial with real coefficients. The number of positive real zeros of f is either the same as the number of sign changes, or less than the number of sign changes by a positive integer. If f of x only has one variation in sign, then f has exactly one positive real integer. So you're going to count how many times the sign actually changes between the coefficients. And then the same for the negative real zeros. The negative real zeros is the same as the number of sign changes, this time in f of negative x. Or it's less than the number of sign changes in f of negative x by a positive integer. And again, if there's only one sign change, then f has exactly one negative real root. Let's go in our books at 387 and let's look at number 37. And it says, use Descartes' rule of sign to determine the possible number of positive and negative real roots for each given function. So we have f of x is equal to 2x to the 4th minus 5x to the 3rd minus x squared minus 6x plus 4. Well, let's first start by counting the number of positive real roots. And we must do that by counting the sign changes. So this is a positive 2. So we go from a positive 2 to a negative, so that's one sign change. Then from a negative to a negative, that didn't change. Negative to a negative, and then a negative to a positive. So we have two sign changes. Which means we can have 2 or 0 positive real roots. Let me go back a slide. It said it's going to be the same as the number of sign changes or less than the number of sign changes by a positive even integer. So you're basically subtracting 2 each time. So we started out with 2. Well, 2 minus 2 gives us 0. So we're going to have 2 or 0 positive real roots. To get the negative roots, the first thing you need to do is evaluate f of negative x. Everywhere you see an x, now you're going to make it negative x. And you get 2x to the 4th power, because the negative to an even power is still going to be positive. Negative to an odd power, well, that's negative times a negative, which makes it positive. And this is what we get. Now let's count the sign change. So this is positive to positive, no sign change. Positive to negative, that's 1. Negative to positive, that's 2. Positive, positive, no sign change. So for the negative real roots, we have 2 sign changes, which means the number of negative real roots is going to be 2 or 0. Remember to subtract 2 and keep going until you get to the 0. So 2 or 0. Sorry about that. Negative real roots.